Oh, hi, TechRabbit here. So now continuing the series on Rust, and now we're going to cover Rust enums and patterns. So let's get into it. And before you're thinking just to cancel this video, you know, enums, I know them from other languages. It's probably exactly the same as us. Rust has it probably implemented in the same way as in other languages. There you go, wrong. Because this is Rust, so I suggest you stick around. So let's have a look. So in its basic form, Rust actually has a simple enum definition, as we are used to seeing it in other languages. So in this case I just created a simple one, enum my ordering, so then it has three values, less, equal, greater. Just wanted to mention that Rust has a lot of enumerator that are predefined in the standard library for different uses. For example, it has an enumerator for defining ordering, and that's in standard compare. And if you just use this use statement, then you actually need to qualify the value that you're going to use. So then you need to actually define the name of the enumerator and then what property value you want to use. So in this case it's less, greater, and equal. Now you can also define a use statement where you import all the children, and then you can actually just you don't need to define the name of the enumerator. In Rust they use the same convention of actually giving a numerical value, an integer value, to each of the enumerator entries. And you can override it. So I just threw in an example here how you can override the value, the default value. The default value starts from 0, and then the next one's 1, and like it usually is in other language. When it comes to size in memory, Rust will try and optimize to take the smallest amount of memory possible. So I threw in a couple examples here. So for example, the size of the ordering enumerator is 1, and the size of my com error is 2. And then a little bit about casting enum values. So in this here we have my com error, bad parallel, and then I'm casting it to an I32 so I can make a direct comparison to its numerical value. But however, the thing is that casting an enum from an integer type directly is not supported in Rust. So they want you to be explicit about the conversion, so when you do that. So in this case I just threw in an example of converting integer value to a specific enum, so you actually have to add the code to do that. Now, however, there are external separate crates which can auto-generate this code for you. So, for example, here we can use the crates num derive along with num traits, and I put some definitions are above main. So, for example, here you can convert from an integer to an enum. So then it adds this kind of functionality. So you have that function available from I32. And then when you want to do it the other way around, convert from enum to integer, then you have the same. So you can actually convert it to the numerical value. Now, Rust enums, you can actually implement things on it. So for example, in this case you can say I can use the derive, and then we add copy, clone, debug, and partial equal capabilities to it. Then we can have methods defined we can define our own methods on enums, which just sounds a bit weird, but in Rust you can. So for example, in the time unit case here, return the unit of this specific time unit. So then you can have this function that actually looks at what the enum value is, the current enum value is, and then it will return the, in this case, a name of the enumerator, as a text string. Return the element of this specific time unit. Okay. And I just put in an example how you should, example of using the time unit. So then you can actually get the name, and then you can get the element. And then, so enum with data, so a timestamp, in this case we're making an example, a timestamp that can deliberately round it off. So our program says, in 6 months ago instead of February the 9th, the specific date. And then we have these creators where you can say in the past and in the future and just now, and that's an enumerator, just time or rough time. And then here I just gave an example how you can use those functions. So this is a little bit more advanced, and one doesn't really, it's kind of strange. Oh wait, you can actually pass parameters to enumerators values. That can feel a bit strange. Yep. Then we have here using struct variants in enums. So here you can define a struct, and then you can actually use structs also in the context of enumerators. So in this case, you say you have a sphere and you have a kobold, and they're different structs. And then here we just see how to use it then. Shape, sphere, center, origin, radius. So this also is a little bit weird that, okay, now, I mean, of course it kind of makes sense. You have an enumerator and it contains like sphere, cuboid, other types of geometrical objects, and then they have their own structs that define their coordinate values, and then you can just you can set those and use those as if it was a normal enumerator. So moving on, so we have 3 kinds of enum variant types, and there is variants with no data, and corresponds to unit-like structs. Tuple variants look and function like tuple structs, and struct variants, they have curly braces and name fields. And then the thing is, a single enum can have variants of all 3 types. So this is can be both good and bad. And then all constructors of fields of a public enum are automatically public. So for example, here we just I created an imaginary one. Development status, it's either development status is unknown, it's ongoing, is complicated with a parameter. It's extremely complicated, and this is a struct with certain parameters. So you can get really creative with when you're dealing with enum types in Rust. So I just a little bit for those that are more interested in the memory mapping, then I added this this here so that you can read about. I don't know. Yeah, for those that are not familiar, what I do is that we go through this, and then I post this code on my GitHub site, and then I have a link in the comments, so you can actually go and pick this up and you can study it and yeah, run the code and you know, copy paste it to your applications and stuff. That's the way that works. So rich data structures using enums. So for example, here's that you want to create an enum to be able to encode JSON data. So then we show a hash map, and then we say that this is okay. So this is an enumerator for JSON, and the idea is that this is for each element of the JSON code. So it can be a boolean, it can be a number, it can be a string, it can be an array, or it can be an object, which is a box type, which in itself can be more JSON. And then we can have also that we actually can have generic enums where we don't actually define the type. So this is like, this is a general option, so the type is undefined for what the option is. So it's either none or it's some option. And here you have the same kind of, this is a general result, and the return values of a like generic type, and error is of an error type. Generic data structure, an order collection of types. So here's also that one can just say, okay, this is a binary tree. So it's either a binary tree is empty or non-empty, and then it's a box of something. And so when you do the top level definition, you don't actually define what type's going to be in this. And then this is part of the binary tree. And the idea here is that you're defining a tree node, but you're not defining for what type of data. And then when we're creating some parts, then and then for when you're doing more advanced stuff, then you get into this you get into this boxing methodology, and then you're using smart pointers to create the references. So here we're was non-empty. We're going to find that. Let's see now. Here. So this is the binary tree, so then it's the boxed item. And then here you see we start creating this. So this is the Jupyter tree, and then we put a non-boxed item here. Element is Jupyter, and then it's no references. And then we create a Mercury tree, and there's no references. And then you can actually start building tree structures with this one. So for example, here you can have a Mars tree, and then it refers to Jupyter tree and Mercury tree. And then I've put in some examples where you can actually get into trouble when handling this type of stuff. So for example, element field Mars element. So then it will say, okay, unknown field uncompiled. And the same thing here, even if it looks like it should work, but it will actually not. And then this is also unknown. And then there's like other patterns trying to access fields directly will also fail. So this is the key. So you will be writing code and say, this is fine, and then you'll start compiling and it's like, no. Okay, let's have a little look at patterns. So this is the simplest example, matching only one values. So this is taking rough time, and then it's trying to see, okay, what is it, what enum is it? Is it in the past, or just now, or in the future? And then it handles the formatting of the printout. And here we've added some more example how to use the rough time in English. So, literals, variables, and wildcards as patterns. So I'll just take in a little bit of random functionality here. And then we have struct meadow, and then we add a function to it, count rabbits. So it actually creates, from the randomizer it gets the number of rabbits, and then it creates a random number, which tells you how many rabbits there are. So then we create a meadow, and we count rabbits, and then we pattern match on the value of the rabbit count. So here we can see match rabbit, so it's nothing to say, 0, 1, or n. That. So you can also match on strings. This is expanded on an example I found regarding to handling different types of calendar types. So settings is string, and then we implement in settings, we take so that it has a constructor, and retrieves the value of the field based on name, and then the setter sets the value of the field based on name. And then then we define the function. And the way I did this is I structured it to show you what kind of will work, and how you use the setter in different ways. So for example, you can do here setting set field to Chinese, special case, Roman, does not exist case. So you can actually yourself, when you're testing this, you can actually when you download the code, then you can actually activate and deactivate parts of this just to see how it actually handles the different calendar variants. So then we see here that we have settings set field calendar unknown, and then using getter to get the actual calendar. And then finally we get, after we built that infrastructure with examples of how that is intended to work, then we can actually go and do the example now about the pattern match. So here we say get let calendar match get field the calendar, and then based on the calendar, what type of calendar is it, it sets the return enumerator. I wish it would be possible to go through all this detail in the video, but I think that this is stuff you really need to actually, when you get to this level of the complexity of handling Rust enumerator, then I suggest you download the code and you read through this. So using variables to match, I tried to make examples with descriptions of, what does it actually mean when you're using a variable to match. And here's an example too. Let's see. So I had an example. Okay, what doesn't work? Trying to make the most generic example of what will actually go. What will feel like it's intuitively what you should have, but then it will actually not work. And then here, use a if statement to capture case. And end matching here. So that's the using that solution, and then Example 3 is do not execute the pattern logic if not correct name. In this example, if is the pattern guard. So this is where we actually want to prevent it to go into pattern matching if there is a certain condition or that a certain condition needs to be met before it goes to pattern matching, because if it doesn't protect the pattern matching from certain input, then the pattern matching subsystem will fail. And then they use this ignoring unknown requested calendar name. And then you can't use this escape method if you're using example 2. And as I said, that those are the key examples, and you really need to like sit with it and study this if you're on this level of complexity. So tuple and struct patterns. Tuple pattern, where is my point? So here we say a function describe point, and then it's going to be matching on a point, and then based on how it matches, then it will actually give you a text description of where is my point, or it will describe the point location, so it's at the origin on the x. So a very good example of pattern matching. And then struct pattern. So we have a point, we have the balloon, and then we put a balloon with the location. So we have, and then we actually want to do some pattern matching on it. How to pattern match on selected fields only. And then I'm trying to make some examples here. Struct many fields, and covering also the issue where you have references to handle, because in Rust you get the system where it will actually move values, and then I call it stealing values. So Rust will suddenly steal your value and then it doesn't exist anymore. So you actually have to be able to understand when you need to use a reference definition. So many fields definition here, and then it shows you the pattern matching. Ignore this field, and then this one should have the value of 3, this one will be 5. And then it will say it's not found, otherwise it will not be found. And then there's another variant where you can actually say, okay, cover field 3 and field 5, and then this ... means that ignore all the other fields, so I'm only interested in them. So you don't actually have to do like I did in this first example of declaring all the fields. And then, yeah, this is this reference patterns, avoid moving the values, because you don't want Rust to move the value to another owner, and then you can't use it anymore. So before matching, and then how you work around that problem of making sure that it doesn't get moved. So I put in different examples here. So filters on that field, and then we grab this by reference to void. Move issue. We grab this by value, ignoring that field, and we grab this by value, and then it informs Rust to ignore fields not listed, and then print all the used fields. And then we actually show how that it grabs. So then it grabs those fields as local variables within this block here, and then you can actually modify them. So I made that example also. So you come in, you match on a pattern, you extract certain fields, you edit, you modify those fields, and then and the end you print them out. So you can actually see how the chain works. But as I said, this is very important to actually, when you're getting on, as again, I think when you get to this level of complexity, it's actually important to to actually sit there with the code and run it, and possibly even modify things to really get into how this actually works. But I've given you a starting point. And then I'm using at pattern to get a pointer, example of access char in a string. So we're peeking. It's a little bit. It's a similar pattern matching, but you know, on a more like if it was you were going to go through characters. And then also you can do matching on multiple possibilities. Like here, some, you know, whatever the character are, or none is true. You can use ranges for pattern matching. So if the character you're peeking is within certain values, so then here it's like it says, okay, it's a number, it's a letter, it's a white space. So bind the value to n while also matching the pattern. So this is a special directive, special pattern directive. Oh, spelling mistakes. So where patterns are allowed. Example 1, unpack a struct into 3 new local variables. This is what I was saying, that you have a struct or a pattern, and then you match it, and you want to extract specific fields out of it. Here we're just going to redefine a track, and then create a track instance, and then original destructuring snippet. Print the unpacked value, so it's unpacking these values from the song. Other fields were ignored, so I just put an example here that, okay, it actually doesn't, it only extracts those fields that you said you were interested in. And then example 2, unpack a function argument. That's is a tuple. So here we define distance 2, create some points, calculate distances using our function, and then print the results. Ah, yeah, that was the unpack a function argument. It's a tuple, so that's what it's doing here. I forgot. Okay. And then show tuple destructuring in a let binding. So here we say we extract that, and then we actually get the individual values. And then there's a third example, there are keys and values of a hash map. So I just added that in there. So here we have a document structure, implements the constructor, creation hash maps, inserts and documents. It's iterate over the key values. And then I added also how do you find a specific document. So then it actually uses the get cache map get function to get the specific ID. I also added an example of automatically dereferencing an argument to a closure. So here we have the closure definition. And then I actually added a full example of how it works. So create a vector of numbers. Some using fold, automatic dereferencing. And then also, we're getting to this level, then alternative approaches for the comparison, like how do you want, without dereferencing pattern, using value directly consumes the vector. Because this is the thing in Rust, you know, if you're not careful, then your value, repeating again, then your value will be moved. It'll be stolen if you do code in a certain way. So you always have to keep this in mind. How do I keep my value? If you intend to keep it, then you need to you need to reference it. You need to make sure you know who's the owner of your value. And then there's refutable patterns. Handle just one enum variant specifically. A short example, and then I'd actually added the full example again. Because I think these short things give you like a high level, but then then I also built or made a full example of it, like putting the infrastructure around it to make it easier to understand. So we derive that. We have a user, and then in the user we implement constructor, date of birth, set time of travel, and then we create some instances, and then it's going to go through and check and mark time travelers. And then again, run some code only if a table lookup succeeds. And here's the short version, and then again the long version. And then we have a cache map version. And then we test with the IDs. And then it's looking for if we have a cache hit or not. And then handle cache misses. This is actually a very useful, very small example of how you make a caching solution. And then we have a repeatedly trying something until it succeeds. Very typical if you have like a TCP/IP or an network communication or something. And this I made a simple CAPTCHA example here where it iterates and tries again until it goes through. And then manually loop over an iterator. Short version here again. Log failed attempts. Present CAPTCHA challenge to user. Retry until successful verification. And at the end I added how do you actually populate the binary tree. However, I do want to note that we're going to, in upcoming editions, we're going to actually go into more detail on this binary tree building and stuff. So this is just like a heads up on that part. But here you can see how it's actually building the, how it's populating the binary tree. So here you can actually see how it actually does that. This is the so here we're implementing an add, specific add function, so you can actually add stuff on the fly. So, hope you found this interesting. Sorry for the background noise, it's very hot in here, so I've had to have a bit of extra fans running. I hope that wasn't too disturbing. And but I do heavily suggest that you take this code and you read through it, and then you run it yourself and do some testing yourself, because I don't think just based on this, 15 minutes, on this short video, it's possible to really get to grips with the details. But I'm hoping I made so many variants of the examples that you can actually pick and choose what you're interested in, and that it will alert you to what you would need to study further when it comes to the enum handling and pattern matching details. So, see you in the next one, and happy hacking.